I don't know about you, but during this quarantine time, I've been watching a lot of Netflix or CBS streaming. I've been watching Picard, and every time I go to a new episode, it always starts off with previously on Picard, and then they would recap the previous episode. So what I'm going to do now is recap the previous video so we can continue. So previously on Bar Cutoff, we discussed the concept of development length. And the development length was the length of the bar that needed to be embedded into concrete so that the bar would break before it slipped out. And there were two possibilities. You could have the straight bar here pulling out of the cantilever, or you could have this hooked portion pull out of the column. And so today on reinforced concrete bar cutoffs, we're going to talk about straight bars. And what we want to figure out is how long, we're doing this one right here. How long does that bar need to be so that it doesn't pull out? And so before we do that, I want to talk about an analogy. So, okay, let's say we're playing tug-of-war. There we go. The people versus the beam. Okay. What I really wanted was the beam to be, the beam is backwards. I wanted it to look just like the people. But anyway, can you see that the people pulling on the bar is very similar to that bar in the concrete? And every person on there, let's say, is pulling, I don't know, 50 pounds. Similarly, every, I don't know, foot, or let's say every foot of the bar is gripping with 50 pounds. So can you see here we have 1, 2, 3, 4, 5, 6, 7, 8, 10 people. And so let's say we had 10 feet of beam. And so we'd have, we would have 1 foot, 2 foot, 3 foot, 4 foot, 5 foot, feet, 6 feet, 7 feet, 8 feet, 9 feet, 10 feet. And so we would have 10 people pulling on the left. We have 10 feet pulling on the right. And so can you see here, this person, let me change to what color should I use? White. I think white will show up on the picture. Okay, so that person's pulling with 10 pounds, or no, what did I say? 50 pounds. That person's pulling with 50. That person's pulling with 50. That person's pulling with 50, etc., right? So each person is adding a little more onto the rope. Okay, there we go. And they're not evenly distributed, but you get the picture. Okay, so everybody's pulling with 10 feet. So right here on the rope, what did I just say? Every person's pulling with 50 pounds. So right there on the rope, there's 50 pounds, right? Right here on the rope, there's 2 people behind this part. So there's 100 pounds, right? Right here on the rope, there's 3 people behind it. There's 150, 200, 250, 300. And so all the way up to here, we're up to 500 pounds because we had 10 people. And so what we kind of need to know, we need to know how much each person can pull. On the other side, what we kind of need to know here is how much can each foot of concrete pull, or what is the grip strength of 1 foot of concrete? Is that 50 pounds? 100 pounds? What is it? Okay. And once we know how many pounds per foot it will hold, and we know the breaking strength of the rope, right? We can know how many feet we needed to have. So for example, let's say the rope does break at 500 pounds and it is 50 pounds per foot. We would need 10 feet of the bar in there. I totally just made up that 50 pounds because it's easy to add. That's what we really need to know. And so, by the way, this is a total side note. Tug-of-war is outlawed in many states, especially for kids, because you can get massive tug-of-war games with like 100 people on each side. And so if you have 100 people pulling, you can, kid could pull 50 pounds easy. And that's 5,000 pounds in the rope. And if you are this person here in the front, that part of the rope right in front of you is holding 5,000 pounds. It's super dangerous. Of course, never ever wrap your arm around the rope. It'll be pulling 5,000 pounds and just snap your arm in half. And this is not a hoax. It's a true story. In Taiwan, I think it was in the 90s or 70s, they were having some big festival. It was like 1,000 people tug-of-war. And it was this huge, gigantic rope. The rope snapped and there was, there's potential energy in the rope. And when that potential energy got released, the velocity was high enough when it snapped, and this is a true story, the first two guys' arms got ripped off. And if you don't believe me, I have a photo of the guy lying on the ground with his arm next to him. It's gruesome. So this is horrible. In pre-stressed concrete, you have the same thing. When you pull a strand, and the strand snaps, it's super, super dangerous. Anyway, this is the concept of development length. We need to know how much per foot the concrete can grip. Once we know that, we can sort of figure out how long the bar needs to be embedded so it'll break before you lose your grip. Okay, so how do we figure out this magic number, 50 pounds per foot, 100 pounds per foot? We're going to have to do experiments. But let's make a math model first. So here's the ideal situation. And so let's say this is the third person on the rope. So that person is pulling up to that point with three people, there's 150 pounds, right? And this represents the fourth person who can pull another 50. So in front of the fourth person, there's 250 pounds. Okay, does that make sense? Go back to the picture. I divided wrong. What did I just say? 150, there. Okay, so here's the third person. So and there's the 150. Here's the fourth person. And so now it's 200 just in front of the fourth person. So here's the bar. The third person up until there is 150. The fourth person adds on another 50. And so now the rope has 200. Okay, that's this concept here. But we don't have people, we have stress. And we don't have persons, we have length of rope. So what we have here, here's a certain stress. Here's the next person, which is a incremental length, a foot, an inch. We're just going to say delta X. And so in front of that extra person or that extra length, you're going to have the original amount, the 150, plus the extra. Okay? And so what we want to find out is how much is that extra. Okay? So it's kind of easy, but it's in stresses and we need to convert it to forces. Okay, so on this side, going to the right, we have this stress, Fs plus the extra times the area of the bar, pi d squared over 4. And on this side, going to the left, we have that stress. It's the same bar, so the same area. And so like in our example, this was 150, that was 100. That means that that extra fourth person was pulling with 50, right? And so the difference has to be the delta force, okay? Okay. And this is what we're gonna call the stress, the bond stress. That's the grip stress. Now, the area that the bond stress works on is the surface of the bar. You're trying to grab onto the rope. And so it's this area here. It's the area outside of the bar, right? And that's what you're gripping on. And so that area is the perimeter, pi d, times the length, delta x, right? That green surface area around the outside of the bar is the perimeter times the length. It's, for example, if you were painting it, that's the area that the paint would cover. And what we're trying to figure out is what's this bond stress, okay? Is it 50 pounds per foot? We need to figure this out. Okay, well, very nicely, the Fs cancels out. And in our little example, you had 150 on one side, 200 on the other side. The 150 would cancel out. So anyway, here we go. The Fs times the area cancels out. So you get the delta Fs. Okay, so that's going to be the 50, right? Or what did I do wrong here? I'm sorry. In our example, on the left side, it was 150, I think. I mean, what were we talking about? 150 and 200. And on the right side, the bigger one was 200. It wasn't 150, it was 200 and 150. But the difference was 50. So delta Fs, the 50, okay, because the 150 cancels out, okay? So make sure you understand. This will cancel that out, okay? So you're left with delta Fs times the area of the bar will equal mu times the perimeter. And we're trying to solve for this mu. But before we do that, let's just do a little bit of algebra. Cancel out the pi's, cancel out one of the d's, okay? And so this is delta Fs over delta x. That's the 50 pounds. So how much do you change the force per length? Or that was, each person could grab 50. So that delta Fs over delta x is how much you're increasing. But instead of per person, it's per foot, okay? So that's how much you're increasing the force in the rope per person, or how much you're increasing the force in the bar per foot. And it's equal to this bond stress. It's the stress, the friction on the outside of the bar, on that green painted surface, okay? And so what we're saying, and this makes sense, the amount you could pull on the rope depends on how strong your grip is. It's not actually 50 pounds per person because everybody's has a different strength, right? And I don't know the strategy in tug-of-war if you put your strongest person in the front or the back, but we all know that different people can pull with different amounts. And so this 50 pounds, so in our example, this was the 50 pounds per person. That actually depends, right, on the person. Similarly, the amount you can pull per foot on the bar, it depends on your grip strength. And so there's two things. There's this grip strength, which is the friction stress on that green area, but also it's inversely proportional to the diameter. So, it's harder to grip a bigger rope. So when the diameter increases, you can't pull as much. So that 50 pounds might go down to 40 pounds. And this is where people make unwise decisions. The rope is too big to grip, or they have poor grip strength. and they'll wrap their arm around the rope to get a better grip. And that's just, you don't ever do that with any kind of rope, right? You just will burn your arm at the least, and at the worst you could break your arm. Okay, so anyway, this here is how tightly you can grip the bar. And so obviously the better grip strength you have, the more pounds per foot you can grip, or the stronger each person is. And this is the diameter of the bar or the rope. The bigger the bar is, the harder it is to grip. Okay, so this is a key thing in principle that we want to know. If you have a stronger grip, you can hold more per foot, which means you can put less embedment, right? So the more you can hold per foot, the bar doesn't have to be embedded as long. Or the bigger the bar, the weaker your grip will be, and so you have to have more bar length embedded into the concrete. Okay, so this is a theory, and so then we have to do some experiments to see if this is true.